Welcome to the technical deep dive of MTF. In this video, we'll explore how MTF redefines channel capacity and efficiency, unlocking new potential for wireless networks. First, what is MTF? The M stands for mask matched, the T stands for time limited, and the F stands for finite access time degrees of freedom. But what is in the name? Well, the name summarizes the technology. Let's start by explaining the meaning of finite access time degrees of freedom. And to answer that, we need to ask an important question. Which communication system provides access to an arbitrarily large number of finite access time degrees of freedom? That is, the ability to use many independent signal components within a limited duration. Is that achievable with a band-limited system or a time-limited system? The only effective solution is a time-limited communication system. Finite access time degrees of freedom refer to the many independent signal components that fit within a fixed time window T. Instead of sending one continuous waveform, we split T into multiple short pulses. By sampling more frequently within T, we embed additional information into each pulse, dramatically increasing capacity. Unlike band-limited systems, constrained by a limited frequency range, a time-limited system leverages these short, distinct pulses to unlock a far greater number of usable dimensions for transmission. How do we harness the enormous number of independent finite access time degrees of freedom? That's the secret sauce of MTF technology. We generate a unique pseudo-random MTF code for each degree of freedom, ensuring each one is individually coded. But it's crucial that each resulting signal also meets the FCC mask, meaning it remains within the allowed frequency and power limits of the chosen band to avoid interference. The pseudo-random code is generated in 3 steps to maximize capacity while meeting the FCC requirements. First, the expanding process replicates and interpolates a base pulse across time, creating a large number of finite access time degrees of freedom. Next, the enhancing process balances the power across these degrees of freedom. Finally, the randomizing process assigns each degree of freedom a unique pseudo-random phase, ensuring statistical independence and compliance with the required spectral mask. How do we comply with the FCC? The figure shows the spectral mask for the unlicensed ISM bands, also known as Part 15. For a time-limited system, the concept of bandwidth isn't rigidly defined. However, the FCC clearly specifies how to measure occupied and out-of-band regions as seen here. MTF ensures all out-of-band emissions remain within that mask by carefully shaping each time-limited signal. Rather than relying on wide channels for capacity, MTF leverages a large number of time-based degrees of freedom, letting it achieve high throughput even in narrower channels. In this way, MTF stays fully within FCC limits while delivering performance beyond what conventional band-limited systems can offer. Let's dive a bit deeper into how we expand, enhance, and randomize our channels. Starting with expansion, we achieve this in 2 complementary steps. First, we shape the base time-limited signal so that it naturally fits within the FCC mask, ensuring it stays within the allowed frequency and power limits. Then, we insert additional frequency components into the signal by carefully reallocating power from the original frequencies. In effect, we carve out new frequency slots, say from A to B, B to C, and C to D, without exceeding our overall power constraints. This dual process lets us pack many more finite access time dimensions into the same time window, dramatically boosting capacity compared to traditional band-limited systems. Next, how do we enhance? Once we've expanded our finite access time degrees of freedom, we optimize the power distribution across the spectrum. In this step, we reallocate power from frequency bins with surplus energy to those with less, creating a more uniform spectral profile. This equalization is key. It minimizes the variation among these independent signal components and maximizes overall capacity. In particular, we focus on the frequency region below 40 dB, ensuring that even the far-out emissions comply with the FCC mask while fully exploiting the available bandwidth. Lastly, how do we randomize? Once we've expanded and enhanced our channels, we assign each frequency component a unique random phase, represented by terms like e to the j theta 1, e to the j theta 2, and so on. These phases come from a zero-mean random distribution, ideally Gaussian, effectively creating a polyphase code across the frequency domain. By equalizing amplitudes and randomizing phases, each channel remains decorrelated from the others, minimizing interference and ensuring we stay within the FCC mask while maximizing capacity. Now that we understand how this code is generated, let's see how it's implemented in practice. Step 1. The transmitter shares its unique MTF code with the receiver through a predefined handshake, ensuring both ends are synchronized. Step 2. The transmitter applies its unique code across all its independent finite access time degrees of freedom, encoding its messages over multiple independent dimensions simultaneously. Step 3. The receiver decodes the composite signal using the same unique code, accurately recovering the transmitted data. Given all this groundwork, expanding, enhancing, and randomizing our channels, we now turn to a key question. What is the capacity of MTF technology? Shannon's capacity formula applies to band-limited systems, but it doesn't hold when a system is time-limited. By leveraging the time-limited nature of our signals and optimizing our pseudo-random code design, MTF technology achieves a significant capacity boost over Shannon's limit. This is illustrated in the figure, where Shannon's capacity is shown in blue and the enhanced MTF capacity in red. Let's discuss the results. When we compare MTF technology to 5G, the improvements are truly remarkable, featuring increased bandwidth efficiency, enhanced connection density, and an astounding reduction in network energy consumption. In conclusion, MTF technology delivers a significant boost in channel capacity beyond Shannon's limit while adhering to FCC spectral requirements, achieved through the use of uniquely generated MTF codes. Thank you for watching this technical exploration of MTF. To learn more about this breakthrough technology, please contact us at info@mtfcom.com